In addition to estimating a population's central tendency, it is important to estimate the variation of the population's individual values. For example, the screen shows two histograms. Each portrays the distribution of 20 repair times in days for personal computers at a major service center. Because the mean, median, and mode for each distribution equals 4 days, the measures of central tendency do not indicate any difference between the American and national service centers. However, the repair time for the American Service Center are clustered quite closely together, whereas the repair times for the National Service Center are spread far apart. That means the repair time might be as little as 1 day, but could be as long as 7 days. Therefore, we need measures of variation to express how the two distributions differ. We will look at 3 measures of variation: the range, variance, and standard deviation. The range is just the largest minus the smallest. The variance is the average of the squared deviations of all the population measurements from the population mean. The standard deviation is always just the square root of the variance. The range measures the interval spanned by all the data. From the figure we saw earlier, the smallest and largest repair times for the American Service Center are 3 days and 5 days. Therefore, the range is 5 minus 3 equals 2 days. On the other hand, the range for the National Service Center is 7 minus 1 equals 6 days. The National Service Center's larger range indicates that this service center's repair times exhibit more variation. You would expect this since the graph for the National Service Center is wider. The variance is computed differently for population data than it is for sample data. For population data, each observation is subtracted from the population mean and the resulting value squared. Once all of these values are computed, the numbers are summed and then divided by the population size, uppercase N. The resulting value is represented by the Greek letter sigma with a squared symbol after it. This is called sigma squared. For sample data, each observation is subtracted from the sample mean and the resulting value squared. Once all of these values are computed, the numbers are summed and then divided not by the sample size, lowercase n, but rather by n minus 1. The resulting value is represented by the English letter S squared. The sample variance, S squared, is a point estimate for the population variance, sigma squared. Regardless of how the variance is computed, the standard deviation is always simply the positive square root of the variance. The population standard deviation is the square root of the population variance and is represented by the Greek letter sigma. The sample standard deviation is the square root of the sample variance and is represented by the English letter S. By way of example, we will use the data on Chris's class size from the textbook. Chris is taking 5 classes with size 60, 41, 15, 30, and 34 respectively. These are all the classes Chris has taken, so this is a population. The population mean is 36. To find the variance, we subtract the population mean of 36 from each data point and square the results. We then add those values together for a total of 1,082. Since this is a population, we divide by the population size of 5 to obtain a variance of 216.4. The population standard deviation is just the square root of 216.4 or 14.71. The screen shows the calculation of the sample variance and sample standard deviation for the gas mileages for the first 5 cars from the textbook. First, we calculate the sample mean of 31.26. Next, we take each of the 5 observations and subtract 31.26 from it. Each of those values is then squared, and we sum them to get a total of 2.572. Dividing by the sample size of 5 minus 1, or 4, gives us a sample variance of 0.643. Taking the square root of 0.643 gives us a sample standard deviation of 0.8019.